Thank you so much, and thank you to the organizers for arranging this wonderful school. So, what I'm going to talk about over the set of the next 5 lectures is driven quantum systems. Okay, so let me give you a brief overview of what I hope to achieve, and then we will move along. Okay. So here is the goal. For the first 4 lectures, I'm going to focus on a very specific form of driving. I'm going to talk about periodically driven systems, and in particular, so the first 4 lectures will be on periodically driven systems. So, as I will introduce to you, these are also called Floquet systems. I will tell you in great details how to analyze these systems, how to come up with an effective description of these systems, and why are these systems interesting. In the very end, the 5th lecture, we will go beyond Floquet and talk about aperiodically driven systems. So I'll give you a sort of brief introduction to how that works. So, quasi-periodic drives, structured random drives, etc. For simplicity and for sort of completeness, our focus will be on isolated systems. So I'm not going to consider a dissipative coupling to the environment, even though that is a very interesting sort of direction of work. Instead, I'm going to build everything up for isolated systems. Okay, so this is sort of the goal what I want to do. Okay, with this, let me start. And since most of our focus is going to be on periodically driven systems, let's start with that. Okay, so the fact that periodic driving can be interesting is perhaps not a fact that should come as a surprise. I mean, even when you do the standard time-dependent perturbation theory in your quantum mechanics course, one of the things that you do is this periodically driven 2-level system that gives rise to Rabi oscillations, right? So periodically driven systems can, of course, so you can see from this very simple example of Rabi oscillations by which you can transfer atoms from one spin state to another, you can already see, or from the ground state to the excited state, and controllably take it beyond this. You can see that periodic driving can be used to control the state of a system. And this particular thing has been the focus of a lot of work over the past 10-15 years. And the setup is the following. The setup is a periodically driven Hamiltonian, which is being driven by a drive period of T, capital T. Okay. And then what we want to do is we want to solve the Schrodinger equation that describes the system, right? So we want to solve the thing is that I have incorporated the tutorial within the lectures, so I thought that it would be better if I give examples instead of just going on building formalism. So yeah, so think of every lecture as a lecture plus tutorial in some sense. Okay. So we want to solve the Schrodinger equation. This is our basic setup. So how do we go about doing this? What is the solution to this Schrodinger equation? So turns out that there is a very nice way to represent the solutions to this equation. The solutions to this takes the form psi of t is sum over n Cn e to the power minus I E n t phi n t, where phi n t plus t is equal to phi n t. Okay. Let me walk you through the structure of this a little bit. So when we think about purely time independent Hamiltonians, right, there what we have is this are the eigenstates of the Hamiltonian, right? So there is no time dependence here, and then we just evolve with the e to the power minus I E n t, right? For a generic time dependent Hamiltonian, you have to write down the Dyson series, right? You cannot just have such a nice closed form. For periodically driven systems, you seem to sort of have a structure which is similar to that of this kind of time independent system, in the sense that you have these energies here which are not time dependent, okay? And what these are I will come to in a minute. But you also have a time dependent piece here which has periodicity in time, right? So this is the structure that it evolves with. So one thing that comes out nicely here is this, you can see that this evolution is sort of split into two parts. There is one piece of information that is inside this that captures what happens within a period from 0 to t, because it repeats after every period, right? So there is one piece which captures what is happening within the period, but there is another piece which seems to be something that does not care about what is happening inside, right? So this will give us bring us to let's go to this, what is this En, okay? So yes,
you should confine to these two.
Acha.
You can go up. No, you can
Okay, so so where
no, here. Here, here.
Ah.
This one will
Oh,
come, and this one will bring it down.
oh, okay. Oh, okay, fantastic. Okay. Oh, good. I can continue here. Yeah, I'm still used to the more manual such boards where you finish and put it up. So I was wondering how do you put it up? Good. Okay. So then the question is, how do I define this En, right? So to do this, let me define for you what this En is. So what I want to do is I want to find the time evolution over one time period. Okay, so this evolution operator is called the Floquet unitary, and this evolution operator takes this form of a time ordered exponential right.
I have a question.
Yes.
The solution, does the solution also obeys for suits for not periodical without the last part?
Without the last part, no. See, if you generically have an aperiodical driven system, what you have to do is you have to obtain this kind of time ordered exponential, right, for a generic system, and then evolve it. Okay, so you are not going to generically get a closed form. But as long as I have a periodically driven system, you would get a closed form. Maybe one thing I should briefly mention, even if you have not seen periodically driven systems before, many of you have probably gone through a condensed matter class, and one of the things that happens there is you look at a system which has some kind of periodic potential in space. Vx is equal to Vx plus A, right? So if you remember there, these block wave kind of solutions that you get something exactly like this, okay? So this structure is not at all different from that. So these are also often called the Floquet block solutions. This form of a differential equation was first solved by Gaston Floquet way back in the 19th century, late 19th century. So that's why these are called Floquet systems. So basically, the fact that I have a periodic dependence allows me to write down such closed forms, just like in condensed matter. The fact that your spatial potential has a periodic dependence that enables you to write it down in a particular form that enables you to do band theory, right?
The craving doesn't change the energy of the eigensphere.
I'll come to that. That is a tricky thing which we'll get to. So the first thing is, how do I define the eigenstate? After all, you see, this phi n is a function of t. I would have defined an energy of an eigenstate if phi n's were not a function of t, right? So, but this nonetheless is something that does not depend on time. The energy does not depend on time. So it must be it must be an eigenstate of something which is, or eigenvalue of something which is a time independent operator, right? What is the time independent operator? For that, let us look at this time evolution over one period, okay? So this, you can imagine that this is something that will be connected to this ENs, because after all, as I told you, that there are two pieces here, one that corresponds to the dynamics that is happening within the time period, and then the other is something that is an overall dynamics, right? So this over here captures what is called the stroboscopic dynamics. So stroboscopic dynamics is, I want to look at the system periodically. I want to look at it at time 0, t, 2t, 3t, 4t, etc. Right? So now how you find this is its own difficult thing, which we will come to in the next lecture. But suppose you know what is the way to find this, then I can write from UF as some e to the power minus IT HF, right? And from there I can obtain what is called a Floquet Hamiltonian, which is minus I by T log of UF. Okay. Now, these ENs are actually the eigenvalues of HF, okay. And these things Cn there, this is equal to the overlap of the initial state with these phi's at t equals 0, phi n's at t equals 0. Okay. I'll prove this. I will try to tell you how this happens. But this will be the structure that it will take. Okay. So a natural thing then is that UF becomes sum over n e to the power minus I ENT phi n 0, phi n 0. Okay. So, mind you, I have not proven this part yet. I will come to it. But is this structure clear? Okay. Yes.
For the eigenvalues, are they defined modulo 2i's and factor?
Yes. Very good. So again, they are defined modulo 2 pi, because naturally 2 pi by t, because of course I'm reading it off from there, so the eigenvalues have to lie on a circle. Okay. This has some very drastic consequences. One of the consequences is that in flow case systems, energy is not conserved. Okay. But we will, again, we will come to this specific thing very, when we look at how we obtain UF. Okay. So let me, this is not very crucial. Let me get this off. So let me look at how one derives this, right? So suppose you are interested in looking at the state of the system at some, firstly, if you're interested in looking at the state of the system at some time mt, so suppose you are interested in psi mt, where m is an integer, right? This, you can imagine, is easy. It's uf to the power n psi 0, right? So this is very easy. So this part looks exactly like a standard time evolution, right? So you can just write this as sum over n Cn e to the power minus I nmt find 0. Okay. So this is easy. This comes directly. Now we get to the slightly trickier part. If you're yes, En. Yes, thank you. So now we get to the slightly trickier part where we are now interested in some time which is between two periods. Okay. So suppose t equals mt plus t naught, where t naught lies between 0 and t. Okay. The claim is that this form also holds there. Okay. How do I see this? So what I have to do then is the following. Psi at mt plus t naught is the following. It is u acting on this, which in turn I can now split it into two parts. Right? So this is clear. I'm just splitting it into two parts, 0 evolution from 0 to mt and then mt to mt plus t. Okay, sorry, let's get this up. Okay. So let's follow from here. Okay. So what do I have? I have, let me call this part of the operator some u tilde. Okay, this is just for my simplicity. So the result of this is u tilde acting on this, right? Good? Okay.
So this phi n's are the eigenstates of UF.
That's right. Phi n's are the eigenstates of UF. Yes. So now, yeah, sorry, go ahead. Yeah, so now what I do is I just add the plus T0 and separate this out. Okay. Now I take the U tilde in, act it on this. Okay. This part? This one? So I'm splitting it into two parts. So I'm doing the time evolution up to the nearest stroboscopic point, and then I'm going inside the period. Okay? Yes. Yes. Yes.
So this phi n's are also evolving, but they're evolving in a global phase, or?
No. So see, phi n zeros, I have, as I mentioned, these are the eigenstates of UF. Okay. Now, I have a relation that phi n t plus capital T, which, as you see here, must be equal to phi n of t, which means phi n of 0 is phi n of t equals phi n of 2t and so on. So phi n zeros are just that. Okay. Now, what I'm going to give you now is what exactly is phi n of t, any t. Okay. So, huh?
Not in after a period, but
At any time. Exactly. So phi n of t generically is, so very good. So this is exactly what you have. Phi n of t, see the way I have broken this up, I have this piece which I have written down, I have this piece, and then I have this acting on this, which tells, yes, thank you. Yes. Oh no, sorry, I didn't want to give m. This is a general t. So see, this was mt plus t naught. Yeah. So this is just the t. T as defined as mt plus t naught, right? Okay. This is literally my definition of phi n t. So you can see that phi n t only depends on t naught actually. It does not depend on anything else. And because here I only have e to the power minus I n t naught, and this is the evolution from mt to mt plus t naught. And note that because of the periodicity of the function, this is true. U from mt to mt plus t naught is equal to u from 0 to t naught, right? So this over here is just a function of t naught, okay? So this immediately tells me that if I were to look at, if I were to take psi of t plus t, if I wanted to add another capital T here, that this would be equal to phi n t plus capital T, but then it would correspond to the same t naught, right? Is this argument clear? So this only depends on t naught. Why am I not writing here? Sir. Oh, so what I want to say is that psi n of t only depends on t naught. And why is this important? I have made this claim that phi n of t plus t has to be equal to phi n of t, right? Since this only depends on t naught, this follows directly. Because you see, I had gone from I had defined my T naught to be the time period after the drive, right? So the fact that is only phi n of T naught automatically implies this. Okay? So this is where what I wanted to prove. So this is why we know that, yes, go ahead please.
So, this phi is
Yeah.
the eigenfunction of the stroboscopic Hamiltonian and
So phi ENs are the eigenstates of the stroboscopic Hamiltonian. Phi n 0 are the eigenstates of the stroboscopic Hamiltonian. Phi n t, which is, as mentioned, is actually phi n t naught. If I am looking at any general t, this is defined through this. So this is, so what it is really is the stroboscopic the eigenstate of the stroboscopic Hamiltonian being evolved within that period. That is the general phi n t. Okay? Yes, please.
Do they satisfy completeness relation all the time?
Yes, they do.
And the form of U delta is not known?
The form of U tilde is known. It's this. We have to compute it naturally, but this is the form of U tilde. So U tilde is basically this. This is what I had written down as U tilde. This.
Okay. I meant more explicitly, we don't know yet.
That will depend on the problem at hand. Generically, it's a difficult thing. You have to, for a generic system, you have to write down a sort of Trotter expansion and actually find it. There are often certain classes of drives, again, which we will come to, where which are called basically kicked sort of drives, where or square pulses, where basically your Hamiltonian does not change for a certain section of the period. So in those cases, you can actually write this down more easily. Okay.
So Sayan,
Yes.
so strategically what I should be doing
Hmm.
is, given this driven system,
Yeah.
we first construct this operator UF.
That's right.
Given UF, I compute its eigenstates and
Yes.
its eigenvalues.
That's right.
So that would give me ENs and phi n zeros.
That's right.
Now, if I want to know phi n at any given time,
Yes.
t,
Yeah.
what I need to do is I need to do EI, EN, T0 this, but then I have to multiply by this function U tilde.
That's right.
And U tilde, what is it doing really?
So U tilde, what it is doing is that after the stroboscopic evolution, so there is, so I can split up my evolution into two parts. One is that part that controls stroboscopic evolution, that is HF, but the other is what is happening within the period. Often, as you will, we'll see a little bit, often what we are interested in is actually just the stroboscopic evolution, because often we are interested in systems which are driven with a very high frequency, and so what is happening within the this time in the middle, this does not matter. So often we are interested only in the stroboscopic evolution. There are certain cases when the what is happening in the middle matters, but we won't cover it. But if you want to know psi at any time, this is what you need to do.
No, so what I need to do is, suppose I want to know the phi n t's
Yes,
at a time t which is 5 capital T plus epsilon.
that's right.
So what I do is that up to 5t,
Yes.
I do evolution according to e to the in. Why is it not 5t?
Yeah. See, this is okay.
Because this looks like the U tilde looks like the evolution from 5t to 5t plus epsilon.
Yes.
But then why am I not getting that 5t?
So the 5t was here. Okay. This is this part which is outside. So now what I have done is I have taken it to this T naught. I've added this epsilon here and subtracted it out. Okay. So this is what we get. That there is a thing that I will just mention right now. Actually, what this captures is evolution in a rotated frame. So I will tell you what this rotation is right now. So one of the consequences of Floquet's theorem is that there exists a rotated frame which is time independent, and within that time, there exists a rotated frame within which the time evolution can be described by a time independent Hamiltonian. That time independent Hamiltonian is HF. Yeah. So this becomes the evolution in the rotated frame. But this is, you can also, as you mentioned quite correctly, what we would have to do as a strategy is to first do this evolution and then act it with U tilde. So this is the, yes.
I just evolve it according to the.
Yeah. Yeah. Sorry. Yes, please go ahead.
Can you again explain the last line that we have written and how does it relate to this?
Very good. So up to this point, things are clear, right? Now I can write down this phi n as one column vector. I can write down this U tilde as a matrix, right? So then I can have this matrix act on this column vector. And what I have done then is I have written down, I've taken down this part, e to the power minus I e n t. This has added a component of e to the power I n e n t naught here. And then I also have the U tilde acting on this, right? This U tilde. Okay. So this thing that I have, right? This overall thing which I'm calling now phi n t. My claim is phi n t is actually phi n t naught. It only depends on what is your t naught here. Yeah, the extra bit.
So you're calling this phi n t because the coefficients that are before that expansion, right?
Yes, that's why I'm calling it phi n t. This is for a general t. Okay. This only depends on this extra bit that you have after the stroboscopic evolution. So this naturally means that phi n t plus t has to be equal to phi n t, because phi n t, because this was a phi n t naught. Phi n t was phi n t naught. So phi n t plus t is equal to phi n, let me take it up here. Phi n t plus t is equal to phi n t naught plus t, right? And this again is equal to phi n t naught. So this implies that phi n t plus t is equal to phi n
That is
t.
because the exercise are 2 pi over t module thing, right?
Yes, that's right. So again, I mean, one thing is that, see, there are many similarities of this structure with Bloch's theorem, because it is exactly what this is, right? So you have this where you have one part which is periodic in time, okay? But even if you don't know Bloch's theorem, is the proof of this clear, why this works, right? This part? Okay, let me go through this again.
That's for a large column matrix.
This is a matrix U tilde,
Yeah, that's a
right? This is acting on a vector, right? I am calling this whole thing phi n t. This is just the label that I'm putting in here, right? So that is fine, okay? But the claim here is that what is phi n t? If I look at phi n t is this U tilde acting on e times e to the power I e n t naught acting on phi 0. Now U tilde, which I defined as U going from mt to mt plus t naught, is also equal to U going from 0 to t naught, right? So then U tilde acting on this would give me phi of t naught. This is my definition, Okay, so just like u tilde acting on this gave me phi on, this was my definition of phi and t, but this is actually just something dependent on t naught.
The overall thing is a 5.
See let me retain the e to the power I e n t naught here. Okay, let this u tilde act out this. Overall, earlier, where was my dependence of t coming from? It did not come from t naught. It came from this part, right? This evolution. This only depends on t naught. Okay. So then the claim is that phi of t plus t, right? What is phi of t plus t? Phi of t plus t through this, I know that this is also equal to essentially the evolution from m plus 1t or t to 2t plus t naught. So what I have then for phi of t plus t is essentially this phi of t, because ultimately phi n of t plus t is phi of t naught plus t, which actually only again has to be phi of t naught. If you look at this evolution, it's sort of split into two parts. One is the evolution that is controlled by the stroboscopic Hamiltonian. Then this is the next part. This is technically called the micromotion. This is what is happening within the period. Okay. So this, okay, this is clear? Good? Okay.
So Sayan,
Yes.
suppose I do the proof like this,
Yeah.
that I take it as an answer
Yes.
and put it back into the original equation
Yes.
and demand that this is a solution.
Yes.
Then does this thing emerge out of it?
That does. It does. Absolutely. And in fact, it is one of the things that we will do almost, except that what we will do is, since we know that this is the solution and we actually are interested in calculating what ENs are for a general system, we are going to put this into the Schrodinger equation, and from there we get an eigenvalue equation which we will solve. Okay. So let us.
The one on the left.
This can go up even further, right?
No, try the one on the left.
Yeah. Oh, very good.
We try to provide some entertainment.
Okay. So this structure here that we have, this tells me something else. This tells me that this form in which I have written down things implies that u from any time 0 to some time t, let me call this t, this can be split up into these two parts. Yes. So the fact that I am able to evolve like this implies that the first part of this piece, this Cn e to the power I e n t, implies that there is one evolution which is going to happen like this, e to the power minus I h f t, right? But the fact that you also have this other piece lying around means that you have another unitary that I have, but that unitary has to be periodic, right? So this tells me that this e to the power minus I k t plus t is equal to, or kf t plus t, let me call this, is equal to e to the power minus I kf t. This operator is often called a kick operator because you can see this as a time evolution which is split into two parts, and one evolution here, and then you have something which is acting as a kick. Okay. Now,
K
the
is the module.
sorry.
K is a function of t, not kf into t.
Oh, kf is a function of t. Yes, yes, yes. Kf is a function of t.
Right in the lower.
Oh, yeah. Sorry. Yes, absolutely. Kf is a function of t, not kft. Good. Kf is the extra bit. Kf is this part.
And it has to be periodic because I want that when that extra bit is equal to capital T,
Yeah,
then I should get back.
just this. Yes, exactly. Okay. But there is one thing that actually is very important that sort of comes from this, is that this actually tells us that there, and this again I will prove right now, there exists a rotating frame where the time evolution of the system is governed only by HF. So the fact that this exists actually tells us that such a rotating frame transformation exists. Okay, I will prove this, so don't worry. I'm not just going to give you the statement. Yeah. In fact, that is the first example we'll do. So, yes. The point here is that the reason why I'll sort of belabor this point a little bit is because often we're interested in what is this HF, and sometimes given a particular Hamiltonian, it is possible, by looking at the structure of the Hamiltonian, it is possible to write down this rotating frame transformation, and which will directly give you HF. So I'll do some such examples. Okay. But let me sort of give you this proof of this, which is this is a this may be slightly boring to some of you because you may have thought about rotating frames, but I think it's useful to know this. Okay, so suppose I have this transformation from a lab frame to a rotating frame. So from lab to rotating, I go with a P dagger, and from rotating to lab, I go with a P. Okay. So what's the claim? The claim is that my psi t in the lab frame properly is equal to P of t in the rotating frame. Okay. So just the transformation, which of course tells you that this is u rotation comma 0 psi 0, and this form already tells you that, oh, I have this transformation works in this way, that you have some evolution happening in the rotating frame, and then something that transfers you back to the lab frame, which is sort of the structure here, right? You have a evolution happening, and then you have something which transforms. I will prove this more carefully now. What is this? Yeah. Yes, yes, please go ahead. Effect of rotation is unitary because I'm defining my rotation through a unitary transformation, right? So remember rotations, all this Sakurai chapter 3 kind of thing, which is you have these angular momentums and then you can write it as a rotation.
Saying about a rotated and or a rotating frame.
I'm saying that it's a frame which we are rotating. So if you are worried about Coriolis forces, they will come up. No worries. Yes. Yes.
Can you again tell what is this e raised to minus kft? It's a kick that I understand.
What it is
Where does it come from?
yes, yes, yes. See, it is this part. Let me get back here. Okay. See, I have an evolution operator which looks like this. Let me use this because this exists. Okay. So I have an evolution operator which looks like this. You have Cn e to the power minus I Ent and this part which comes due to the micromotion, right? So that means if I look at the time evolution, the fact that I can decompose it like this implies that I can write down a first part of the time evolution which looks like this. Okay. But then I know that I am not done because the actual evolution is not just this, you also have this acting. So after time evolution by this, you also need to put in something else, okay, which is also an unitary transformation and which has to obey, which will take phi n zeros to phi n t's, but you also know that phi n t plus big T is equal to phi n t, which means that e to the power minus I kf t plus big T equals e to the power minus I kf t. It also, sort of ties up with what Shamik said, that basically I want when t is 0 or at the end of a period, my evolution would only be governed by HF. So this also naturally puts in this set of periodic boundary condition, if you will, that this has to be obeyed. Okay.
Kf just rotates your eigenstates to the time that at that time.
That's right. Yeah. Sorry. Okay, good. Yes, yes, yes. So please ask questions because I know we are just building formalism. So yeah. Yes, yes, please.
This, when you are proving that phi n t plus t equals to phi n t,
Yes.
this is the phi n t, those are phi n 0. Phi 0.
Yes, 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 yes. I have this very bad habit of being sloppy with notation. Yes, these are all phi n zeros.
Phi n t.
Yes, yes, yes. These are all n's. This holds for basically once I have my u, I can from the u I can obtain my HFs, right? The Floquet-Hamiltonian, which has certain eigenvalues and certain eigenvectors. I'm labeling those eigenvectors, and during the time evolution, I'm looking at what is the, this part remains constant, and then this has to obey phi n t plus big T equals phi n t. Okay. Okay. Oh, sorry. Okay, let's continue. Okay. So this was my definition from here. If I look at the time evolution in the lab frame, this is equal to the time evolution of this object. So the psi t in lab frame is just p acting on psi in the rotated frame, just from my definition. This is equal to I p dot, the rotated frame, Okay. So I've just written down Schrodinger's equation. Okay. I have psi t in the lab frame. I've just written it down as P acting on psi t in the rotated frame and just expanded it out, right? So I have a I P dot here, and then I have this P I del T of psi t in the rotated frame, which is just H rotated. Okay. So from here, I immediately get what is the relation between H rotated and H lab. Sorry. This right, yeah. Okay. So the conclusion I draw from this then is this H, I can relate my H rotated to the H lab, right? And how I do it then is I essentially write this back in the lab frame and write this as H psi lab, and from there I can read this off, right? So this is basically, this first part here is just the rotation. The second part is the fictitious force that comes because of transformation. Is this step clear? I can write it down more explicitly.
Do the Hamiltonians H lab and H rho commute with PP dagger?
The Hamiltonians do not need to commute with PP dagger. See, the way that I have the sort of the way that this comes is essentially the following, that this over here, this equation was H lab psi t lab, right? And this I know then is H lab P dagger psi t rotation. No. See. Oh, sorry. This is, sorry. This is HT. Yeah, so, no, you're right. So this is basically HT psi t, okay? And from what I need to do then is, if I have to read off H rotation, I have to multiply by P dagger, right? So this would immediately give me that P dagger H lab P minus I P dagger P dot is equal to this. So there is no, this is a very general expression. This is true for any rotated frame, and this is the standard just rotation. This is the fictitious force. Okay. Yeah.
Is it possible to like let's say in the lab frame the system is having Hamiltonian dynamics, but I go to the rotating frame and it is not just Hamiltonian dynamics?
That
Assumption there.
No, that is not an assumption, because all that we are saying is that we are doing any rotation to any frame can be written down as a unitary transformation. Okay, so this is basically, if you go to this again, my favorite Sakurai chapter 3, you have all this description about Euler angles, and from there how do you make these rotated frame transformations. Modulo all those definitions, one of the things that comes out of it is that any such transformation that I do can be written down as a unitary transformation. And the only assumption that I have made, not an assumption, but that is the only result I have taken. Once I take that result, there is nothing else that I am using actually. So there is no assumption, but I am indeed using that result, that the transformation to this is a result that I am using, that this P is a unitary transformation, but this, I mean, I can't do a better job than what Sakurai has done. So yeah, so I would, if for those of you, I'm sure you've seen this. Also, is very possible that you may not remember all the details. So heavily recommend that you can go back and look at this. But one of the things that I wanted to maybe just briefly mention is that this structure immediately tells you that this HF actually describes what is the evolution in the rotating frame. Okay, and one of the ways to see this then is that if I write down this HF, right? So if I use this as P, okay, and let's say I have a lab frame Hamiltonian, okay, from the lab frame Hamiltonian I want to go to this rotating frame. So then one of the things I will do is that I have this additional piece of P, okay, and then once I am in this rotating frame that is defined through P, then my evolution only happens through e to the power minus IHF. So this is sort of this thing, that psi of t is P of t times u rod. Okay. Yes, please go ahead.
Hamiltonian is time dependent.
Hamiltonian is time dependent.
HF is stationary.
HF is stationary, that's right.
So in the rotating frame, as far as the stroboscopic evolutions are concerned, not stroboscopic.
No, not stroboscopic. Rotating frame, any evolution. Because, see, all that I have done is what I did through this is to tell you first, how a rotating frame Hamiltonian is related to the lab frame Hamiltonian. But then the claim is that if I can write down my, lab frame Hamiltonian as some P of t times the rotating frame Hamiltonian, from there I can obtain the rotating frame Hamiltonian, okay, which will be just given by this. Now, the next thing that I have said is psi of t in the lab, okay. This is given by this kick operator times e to the power minus I HFT. In the same spirit as this equation, then I can write that psi t lab is equal to e to the power minus I KFT, right, times psi tilde t, no problem, right. This psi tilde t is e to the power minus I HFT acting on psi 0. This is the rotating frame. Yes, so psi tilde t So what Floquet's theorem tells you is there exists a rotating frame where your time evolution, your exact time evolution is determined by a time independent Hamiltonian, right? So one of the things that you can do is, if you are able to, suppose somebody gives you a time dependent Hamiltonian and you are able to figure out such a P such that the time independent part of your Hamiltonian gets cancelled out, right? So then whatever you will be left with is the Floquet unitary. Yes.
If we are just looking at the stroboscopic,
Yeah. Yes. Yes.
then these two Hamiltonians must be identical.
They have to be. Yes.
So this P of capital T
Yes.
is identical.
Identity. That's right. So it's rotating with the same period as the driving period.
What
Yes.
about the physicist term that you have there? Right? First term is H rho and H lab. But what about the other?
Yeah. So the fictitious term vanishes at that point. It has to. It has to be 0.
because P dot is 0. P has no time dependence.
So, okay, so what is happening, it's not so much basically P dot being 0, it's this, e to the power minus I kft. So, if I want to set that e to the power minus I kf 0.
I think at stroboscopic time P is identity.
So, what I want to do is the following, I want to put t at t equals 0, this should be identity, right? So, which means that this, yeah, so exactly what Utija was coming to. This P here, which is, so I have this P dot, I have defined this H rod as this P dagger H lab P dot minus I P dagger P dot, right? So the point here is that, so P has to be identity at that point, and P dot has to be 0 at that point. So the fictitious force has to vanish. Yes. Okay. Good. Okay. So maybe let us do a few examples now that we have set up. So is the formalism more or less clear? Good. So we'll do a few examples to sort of clarify some of the things about how one actually calculates these things. Okay. Oops, sorry, I don't want to do that. I want to just go up. Okay. So the first example that I want to do is something, so examples. So the first example that I want to do is something that you are familiar with, and this is the example of Rabi oscillations. So you consider a two-level system H is Bz minus Bz gamma to the power minus I omega t, right, to the power I omega t. Okay. It is actually fairly, so this is a time dependent Hamiltonian, right? This is a familiar from Rabi oscillations, right? There is a very simple and nice P that can get rid of the time dependence here, and that P is basically the following. If you take this, then what will happen is that this P of t acting on these off diagonal terms will kill off the time dependence. So just to tell you how this happens, let's take one of this. Let me just concentrate on this one. So when I act this here, right, so what will happen is that this e to the power minus I omega t sigma z by 2 will pick up e to the power I omega t by 2 plus I omega t by 2 here, and this acting here will pick up another e to the power I omega t by 2, and this will cancel this e to the power minus I omega t. Okay. Is this clear? So this acting on this will give you this e to the power I omega t by 2, this gives you e to the power minus e to the power I omega t by 2, then net result of this is just 0, 1. Huh? This is the PT. All I'm saying is that if I take this PT, I'll tell you that I will show you that I can remove time dependence. Okay. So I wrote this PT and told what I wanted to say was that if I take this Pt, the time dependence of the off diagonal terms go away. I still have this term left, but that with this Pt is something that is not time dependent anymore. Okay, so if you do this P dot acting on this, what will happen is I omega will come out, but this P dagger and P still has this e to the power I omega t by 2 form, they will cancel each other. So you'll get identity from that. So the net result, yes, yes, please.
You write this u of p power 0 as some p times this guy.
Huh.
So p is fixed, p is always uniquely fixed, I mean up to the modulo twice 2 pi.
I mean, yes, so it has to be uniquely fixed because Pt has this unique definition, right? So the point is the following, that in certain cases, so this is the formal structure, this tells you, this guarantees that you will have such a P. Now, one of the things that I would want to sort of emphasize is that sometimes by looking at the structure of the problem, you will be able to read off what the P should be, because what the P is doing is it's killing off the time dependence. Okay, so again, of course, everything is modulo 2 pi, but modulo that you can always, the P that you will get will always be uniquely defined. Yeah.
From this Hamiltonian, for this two-level system,
Yes.
you can also do the same procedure.
You can do the same procedure. The only thing is that what I want to do say is that doing it from the other direction is costly, and if you can guess the form of Pt, then your life becomes simple. Right? Oh, sorry, I keep forgetting how this works. Okay. Okay. So what you end up getting is this kind of thing in the rotated frame. Bz so this additional piece of P dagger P dot actually gives rise to omega by 2 sigma z. Okay. And now this has become a time independent problem. Okay. I'm not going to solve this problem any further except to say that, it's sort of obvious that this, what are the eigenvalues of this I can read off, and from there I can get Rabi oscillations with frequency omega being equal to Bz minus omega by 2 square plus gamma square. Okay. While I am not solving this, this is not so difficult to believe, because if I solve the eigenvalue problem, these are the omegas that come out. Right? These are the eigenvalues that come out. Okay. Let us do some more examples. So this is the part where we transition into almost becoming a tutorial. So what I'm going to do next is two things. So I'm going to talk to you about, of course, an explicitly time dependent problem, but I'm going to actually start off by talking to you about a problem which is time independent, but if we it actually becomes time dependent by doing a rotation, but actually the time dependent problem can give you some insights. Okay, so even though it looks like an awkward thing, it actually turns out to be quite nice. So what is the problem that I'm going to do? I'm going to do this problem of electrons in an electric field. Okay, so, or you can think about it as atoms in a gravitational field. Okay, any of these things. So suppose I have these particles hopping with some tunneling amplitude j in some potential which has been tilted. So I can write this as h equals minus some over j minus j So since this has a gap of j, so every site j has this energy j times delta, right? And then you have the hopping. Okay. So far so good. Okay. I mean this again may not be a surprise to you, but when I first encountered the problem, I was heavily surprised because classically what we expect is typically if I have a particle in a potential and I tilt the potential, it will accelerate. This is my classical expectation, right? If you take a quantum particle in a tilted potential, it localizes. So, huh? Stark localization, yes. So I mean, to me at least, this seemed like a very, very interesting detail when I first learnt it. I will tell you a little bit why one localizes. But you can actually go to a rotating frame, and this rotating frame transformation will give you, I'll tell you first what it will give. It will tell you that you have a HF, a Floquet Hamiltonian, which is localized. And then you have this kick operator, which is accounting for the micromotion. That has a physical manifestation that is something called Bloch oscillations. So if you put electrons in this kind of a tilted field, what would happen is that instead of really accelerating away, it will go and then it will return. Okay? So this phenomena is called Bloch oscillations. And so I will do this transformation, and just because I sort of think is neat, I will tell you how why this should work at least, and I'll tell you why localization is expected when this delta is much larger than any other field.
If I start with the web packet which is localized in one of the
Yes. Yeah.
I would have thought that it would tunnel through and then
It would tunnel and then it would return. So this is the thing that if I okay.
I see. So interfere. Okay. So
Yeah.
it would interfere and that would lead to localization.
So actually, it's not so much interference. So yeah. So there is a mismatch of energy scales here essentially. That yeah. So that prevents you from localization. So what will happen here is that if I had a simple lattice and I let a wave packet go, it would just keep on going because actually all my eigenstates are extended. Once I put it like this, because of this energy mismatch here, actually your tunneling gets suppressed. So if you actually let it go, this will go and then it will return. Another way of seeing this in the which is sort of more semi-classical and is sort of more believable in some sense, is if I look at the band structure E versus K, it has a repetition after 2 pi. So if I set off a wave packet with a particular K, the K will change, but after a while, because of this periodicity of the band structure, the K has to reverse. So yeah. I don't know, when I first encountered it, I was very, very impressed by this problem. So yeah. Okay, this is very old. It was actually done by Stark and Zener back in 1930s. Yeah, okay. Stark and 1 year, also Zener. Yeah, all of these people. Okay, so what is the rotating frame transformation that I will do? So you see, this part of the Hamiltonian is something that we all know. This is just the tight binding model. This is the fly in our ointment. We have to take care of this. So what I want to do is I want to add, or I want to do a rotating frame transformation which will get rid of this. Okay, and when it gets rid of this, we can't really get rid of it. Once we get rid of this, it will come as a phase here. Okay, so what I do is I write down this operator here, okay, sorry, delta j and j. I write down this operator here, okay. The P. Why did I write this as the PT? What I want to do is I want to cancel off this term. So this is typically a spirit of trying to do any kind of frame transformations. Suppose there is one part that I understand, and then there is another part which is causing my problem. So what I want to do is a frame transformation that gets rid of this. Okay. Sometimes I would be able to do an exact frame transformation which works out very well. Occasionally we might be able to do an approximate transformation, but there we may be able to at least expand it in terms of some small parameter and so on. But this is an exact transformation. What it does is it kills off this piece, because when I do that p dagger p dot, right, what will come out is this delta sum over j and j. This will cancel off this piece, right? So I'm not writing it down specifically, but it's clear, right? Okay. Yes, absolutely, yes, yeah. So the only, well, it's not, it is exactly similar to the interaction picture. In some sense, the interaction picture is called the interaction picture because we have h0 plus h int. So this is a generalization of that kind of idea, yes, okay. Good. So I have this. So then what do I get from here? What I get is now, so this takes care of my p dagger p dot, but I am still left with this term, okay. And what happens here in this rotated frame is the following. We end up with a Hamiltonian which is going to look like this. So this whole thing shows up as a phase e to the power I t delta. You might wonder what happened to this j. What happened to it was I had a aj plus 1 dagger aj acting on this. So when I act it over here, one of this gives you a term of j plus 1, the other gives you a term of j, and they subtract out. Okay. The hopping amplitude has been modified.
This is the consequence of the localization.
That is exactly. This is what will, this is, localization can be thought of as exactly this. Because now if your delta is much greater than j, let's say, this is when this is easiest to see, then what I will get is, then I can imagine that this is a system which is being driven very fast. So if I look at the average Hamiltonian, okay, which will be sort of some approximation to the stroboscopic evolution, the average Hamiltonian actually goes to 0, right? So this gives you localization. The other thing is that you can see that this is periodic with period 2 pi by delta, which means that there is micromotion that happens within a period of 2 pi by delta. This micromotion is exactly Bloch oscillation. So the Bloch oscillation period is 2 pi by delta, which means that if I were to leave a particle from here, it would actually go down and return in a period of 2 pi by delta. So even though this was initially a problem that was time independent, and time independent problems are always easier to do, the transformation into the rotated frame actually gives me something nice. It tells me that when delta much greater than j, we get localization. Actually, you get localization always, but this tells you that you will get a very strong localization when delta is much greater than j, and also Bloch oscillations. Micromotion. With a period. localization. The localization argument is that this Hamiltonian is periodic with a period 2 pi by delta. If this delta is very large, we can think about this as a very fast moving thing. So it's a very high frequency oscillation. And then if this is very large, then what I can do is it is reasonable to approximate the stroboscopic evolution purely through the time averaged Hamiltonian. Because imagine that if things are moving very fast, so the time average would be a reasonable approximation for the stroboscopic evolution. If I look at the time averaged of this is a complex thing. So if I take the time averaged of this will go to 0. So that means that your Hamiltonian does not lead to any delocalization of any wave packet, right? So that's why we have localization. Okay.
So the conjugate part, it has the same to the power IT data, right?
That's right. So the conjugate part has e to the power minus IT there. Yeah. So it just is this, that one of these has a dagger j plus 1, the other has a j plus 1. So when you act with this frame transformation, what it is doing is your frame transformation has this j times delta nj. So this then just becomes a j plus 1 minus j, and the other becomes.
When delta is not that large, it's non-reciprocal.
No, it's not non-reciprocal, because this whole thing also comes with a e to the power minus it delta. Yeah, so there's no non-reciprocity here. So doing non-reciprocity is a very hard, again, one may sort of, it's very tempting to think that when I am putting in something, a tilt, then one direction is favored. This is what our classical intuition tells us, and it's very tempting to think that induces non-reciprocity. It does not. Okay, this whole thing is always Hermitian. So actually, there is no non-reciprocity anywhere. So to induce non-reciprocity, you have to introduce some sort of dissipation in some way. So it has to be. It cannot happen with e to the power I t delta. It has to be a t delta. Okay, it has to be a t delta and minus t delta, something like that. That will.
One question.
Yeah.
For the ground state, the localized state will be one of the edge modes.
No. So that is okay. The point is that the thing with a reciprocal or the thing with non-reciprocal hopping is that you have a macroscopic accumulation of states on the edge. Okay. Here, all the states are different localized states. Yes. So yeah. So that is the crucial difference. Yeah. Yes, please.
Can you again say how we interpret block oscillations from the E delta?
Oh, so this is just saying that I did not really infer block oscillations. I said that what I want to say is that there is micromotion here that happen with a period 2 pi by delta, right? Even if I have localization, even if I am in this high delta regime, I still have micromotion that happens with a period of 2 pi by delta. So what this micromotion is in this lab frame picture is actually block oscillations, because what it is telling me is that I have this 0 to t within which, if I am localized, that means that I have to return to the same state at time t. But within 0 to t, I can oscillate. Now in the strong localization regime, there would be something again that you would see, that if you did the actual problem, you could oscillate with some, there is some time for which this will go and return, and the amount that it will go depends on delta. But if you are within this sort of strong, that period is actually 2 pi by delta, okay, and that you can at least infer that in this delta much greater than j, that has to be that has to be an interpretation of the micromotion. So what we were looking at as block oscillations in the lab frame, in this rotated frame, that appears as micromotion. Okay. Yeah. So yeah.
Suppose we take this model
Yes.
When we drive this delta, so then we become this delta as a time dependent.
Yes, very good.
Then this P of t I guess will be in the same form, but time, I mean integration over delta.
Very good.
Then what will happen?
Then what will happen is the next tutorial problem. So. But how are you guys feeling? Because we are at 10:56, so technically almost 1 hour 20. So if you are feeling saturated, we can start off with this problem the next time. Okay? Because I think it's a little involved, and I would want to do 2 examples there. Okay? So let's do that then. Then we for this. The next of this is after lunch, but of course we reconvene after coffee. So then we'll continue this. Okay? Thank you.
Hello. So first, let's thank our speaker.
Thank you.